In the collection of a museum in London, there is a single typed page signed in Pasadena, California on the 6th of February, 1997. 2 of the 3 signatures at the bottom were written by hand, in ink, by men who could still hold a pen. The 3rd is a thumbprint. The page is a bet. 3 physicists, Stephen Hawking, Kip Thorne, and John Preskill, had been arguing for years about what happens to a thing after it falls into a black hole, and they had arrived at the point in an argument where reasonable people stop talking and start writing terms down. Hawking and Thorne took one side, Preskill took the other. Then, because they were physicists and the joke was sitting right there, they specified the prize. The losers would owe the winner an encyclopedia, not any encyclopedia. The document is careful about it, and the phrasing has stayed with me for years. An encyclopedia of the winner's choice, from which information can be recovered at will. They could have written an encyclopedia and left it alone. Instead, they specified the kind, a book that gives back whatever is put into it, reliably, on demand, for as long as the book exists. The prize was chosen to be the exact opposite of the thing under argument. What they were arguing about was whether the universe keeps a record of itself. Put it in the plainest terms available. You have a book, any book, and the fact that it doesn't matter which one turns out to be a substantial part of the problem. You carry it to the edge of a black hole and let go. It falls, it crosses the boundary, and it is gone in the ordinary sense of that word. Nothing you do afterward will bring it back. That much has never been in dispute by anybody. The question underneath the bet is stranger and considerably harder to shake off. When the book is gone, where is the story? The reason this became a 50-year argument rather than a passing curiosity has to do with a claim quantum mechanics makes and does not bend on. Burn the book instead. Set it on fire, watch it go to ash and smoke and heat, and then ask a physicist where the words went. You'll get the same answer every time. The information in that book is still here. It's in the pattern of the smoke, in the precise arrangement of the ash, in the particular light that left the flame and is now several kilometers away and spreading, scattered past any hope of reassembly and present. In principle, and physicists mean something very exact by in principle, you could run the whole room backwards from its final state and recover the page. Not in practice, never in practice, but the universe, as far as anyone can tell, does not permit the alternative. Information gets scrambled, dispersed, buried, rendered permanently unreadable. It does not stop existing. A black hole appears to permit the alternative. That is the entire trouble. From the outside, a black hole formed by collapse is described completely by 3 quantities: how much mass it has, how fast it spins, and what electric charge it carries. That is the whole list. 2 black holes matching on those 3 numbers are identical in every respect anyone can measure, no matter what went into them. One might have formed from a collapsing star, the other from a library, a mountain range, 400,000 years of accumulated dust. Nothing distinguishes them, and nothing ever will. On its own, that's concealment rather than destruction, and concealment breaks no laws. The book is behind a wall. Walls are allowed. What Hawking worked out in 1974 is that the wall doesn't last. Black holes are not permanent fixtures. They radiate, faintly, at temperatures so far below anything the word cold was invented to describe that the comparison stops being useful. And across spans of time that make the present age of the universe look like a rounding error, they thin out and shrink and finally finish. The wall comes down on its own, and the radiation coming off it, as far as the calculation could tell, depends on exactly one property of the black hole: its temperature. Nothing about the star, nothing about the library, nothing about the book. So when the last of it has gone, there is no wall left to be behind, and nothing that came out was carrying the story. Both of those accounts are assembled from physics that works. Quantum mechanics is the most precisely tested description of reality anyone has ever written down, accurate to a dozen decimal places in the places we can check it. General relativity has survived every measurement aimed at it for over a century, including several that nobody expected it to survive. Put the two of them in the same room, point them at a black hole, and they say incompatible things about whether the past is still there. The argument turns 50 this year. The process it concerns, the complete evaporation of a black hole with the mass of our Sun, takes roughly 10 to the 67th years, which is a 1 followed by 67 zeros, and I'd encourage you not to try to feel that number, because it doesn't work. 50 years of argument against a 1 followed by 67 zeros. Whatever the answer turns out to be, it isn't going to arrive by observation. Nobody is ever going to watch this happen. There's a version of all this that ought to feel personal and somehow doesn't. You are, by any description physics can offer, an arrangement of information, an extraordinarily specific one, holding its shape for a while. Everything you have ever done has left traces in the ordinary, irreversible way that everything leaves traces. Heat, motion, light going out in all directions and not coming back. If the universe genuinely cannot delete, then none of that has ever been undone. Unreadable by anything that will ever exist and still not undone. There is a particular quiet that settles in after thinking about this long enough. The universe is not a witness. It has no interest in what happens inside it, no mechanism for caring, and no memory in any sense that involves remembering. But it may, without intending to and without anyone having asked, be a perfect archive, something that has held on to every arrangement of every particle since the beginning, in a form so thoroughly mixed that no reader could ever exist for it. A complete record with nobody to read it. Whether that lands as a comfort or as the loneliest available fact seems to depend entirely on what hour you consider it at. At 3 in the morning it can go either way. What I keep returning to is that the universe would be keeping the record regardless, not for us, not for anything, and would go on keeping it long after there was nothing left that could have read a word. Before we go any further past that boundary, and we're going a long way past it, this is where I ask, if these are the sorts of things you want to keep hearing about, late in the dark, subscribing helps more than it reasonably should. It's quiet. It costs nothing, and it's most of the reason the next one gets made. I'd also like to know what you'd throw in, not the thing you'd want destroyed, the one thing you'd want the universe obliged to hold on to, whether or not anything ever reads it back. Leave it below. I read them. The bet was settled after a fashion. One of the three eventually changed his mind in public, in front of cameras, and handed over a book, and the newspapers reported that the paradox had been solved. It had not been solved. The physicist who won the Encyclopedia was not himself persuaded by the argument that won it for him, and said so at the time. And the third signatory, Kip Thorne, simply declined. He declined to concede, declined to contribute to the prize, and declined to agree that anything had been demonstrated. He has now been declining for 29 years. As recently as 2 years ago, he was still explaining, publicly and patiently, why he isn't convinced. The argument itself is older than the bet by 21 years. It begins properly in 1976 in a paper by Hawking with a title that reads like a weather warning, a breakdown of predictability, and it has been running without interruption ever since. In the autumn of 2025, the people who work on this problem held a meeting that ran for 7 weeks. The stated purpose was to find out whether they agreed with one another. 50 years in, they convened formally to establish what had actually been settled, because the various groups working on it had stopped being able to follow each other's arguments. That is where the question stands now, not at the edge of being answered. Somewhere considerably stranger than that. The bet was signed in 1997, but the crime it was arguing over, and it was framed as a crime, quite deliberately by the man who framed it, had already been committed 25 years earlier in an office at Princeton over a cup of tea that somebody let go cold. What would you have to do to commit a crime the universe itself could not detect? The bar is higher than going unnoticed, which happens constantly and takes no cleverness at all. The bar is leaving nothing behind to be noticed, no trace at any level of description, in any ledger anywhere, permanently, so that physics checked afterward by something with perfect instruments and unlimited patience would come up entirely empty. John Wheeler believed he had found a way to do it, and the discovery bothered him for years. Jadwin Hall, Princeton, sometime around 1970. Wheeler is in his late 50s by then, one of the most consequential physicists of the century, the man who had made the name black hole stick and who had spent a decade insisting that the objects deserved to be taken seriously as physics rather than as mathematical curiosities. Sitting with him is a graduate student named Jacob Bekenstein in his early 20s, who has come to work on precisely this. On the desk, there is tea. Wheeler told this story more than once across the following decades, and the staging drifts a little between tellings, sometimes 2 cups, sometimes one cooling beside a colder one, so hold the details loosely. What stayed constant in every version is what he said about them. Let the hot cup cool and the cold one warm, and leave them side by side until they meet somewhere in the middle. Nothing has been lost. Run the energy accounting, and it balances to the last decimal. The heat that left one went into the other and into the air of the room, and the total is exactly what it was. Something has happened all the same, and it cannot be walked backwards. Before, there was a fact about the world. This cup is hot, that one isn't. Afterward, there is no such fact. The molecules that were moving quickly are now distributed indistinguishably among the ones that weren't, and nothing in that room or in any room will ever sort them out again. That is entropy in the version that matters here. It isn't disorder in the household sense, and the popular framing about messy bedrooms does the concept no favors. Entropy is a count. Given the way a thing looks from outside, this temperature, this pressure, this volume, it measures how many distinct arrangements of the invisible pieces would produce exactly that appearance. A low number means very few arrangements would do, and the outside description therefore pins down almost everything. A high number means an enormous quantity of arrangements are consistent with what you can see, and correspondingly little can be said about which one you actually have. Entropy is a measure of how much has stopped being knowable, and the second law of thermodynamics says the number only goes up. Arthur Eddington put the standing of that law about as bluntly as anyone ever has. If your theory disagrees with Maxwell's equations, so much the worse for Maxwell, and these things happen. If it disagrees with the second law, there is nothing to be done for you. Physicists have generally taken his side. It is the law you do not get to break. Wheeler's remark, as Bekenstein recalled it afterward, went like this: Jacob, if a black hole comes by, I can drop both teacups into the black hole and conceal the evidence of my crime. Follow what that would actually mean. The cups go over the edge, and the black hole becomes very slightly heavier, and that is the complete observable consequence of the act. If you were outside with the finest instruments that will ever be built, you'd have no way of establishing what had gone in. Not the shape of it, not the temperature, not whether the 2 cups had been mixed or kept apart, not whether anything had been dropped in at all beyond a certain quantity of mass. The entropy of the tea, all that unsorted molecular history, goes past the boundary and stops being part of the universe's accounts. The number that only goes up would have gone down. Quietly, with no one able to file a complaint, because no one outside could construct the evidence that a complaint was warranted. Every ordinary method of disposing of evidence falls short of this, and the shortfall is the whole point. Shred the documents and they're in the bin in 800 strips, and somebody sufficiently patient with sufficiently good software puts them back together. This has happened in real investigations more than once, and the reconstructions held up. Dissolve them and the molecules are in the solution. Scatter them across a landfill, and they are, tediously and expensively, still in the landfill. The standard everywhere else in physics is that evidence gets made difficult. Wheeler was describing something with no equivalent anywhere in ordinary experience, a location you could put a fact into, such that afterward there was no fact. Under the physics as it stood in 1970, this worked. That is the part to sit with for a moment. The most secure law in the natural sciences, the one Eddington said he would back against all the others, had a loophole, and the loophole was shaped like a black hole. Anyone with access to one could run the entropy of the universe backwards indefinitely, and no audit anywhere in the cosmos would register the theft. Bekenstein gave the scheme a name, Wheeler's Demon, and went away to think about it. He came back some months later with the answer, and the answer was that the crime doesn't work. The reasoning is elegant enough that it still reads as slightly unfair. If the second law is going to survive, then whatever you drop in must raise the black hole's own entropy by at least as much as the universe lost, which requires that a black hole have entropy in the first place, that this object, describable in 3 numbers, with no visible parts and no internal structure anyone could point to, nonetheless has a count of hidden arrangements attached to it. So Bekenstein went looking for something about a black hole that behaves the way entropy behaves. There was already a result sitting in the literature with exactly the right shape, and it had been proved 2 years earlier by Stephen Hawking. The area of a black hole's event horizon never decreases. Not in any process anyone could construct. Throw matter in, and the area grows. Collide 2 black holes together, and the horizon of the wreckage that results is larger than the 2 you started with, added together. It only ever moves in one direction, which in physics is a rare and conspicuous property, and there was exactly one other quantity anybody knew of that did the same thing. Bekenstein put them next to each other and proposed that they were the same quantity. The entropy of a black hole is its horizon area, in the appropriate units. Drop the T in and the horizon swells by a precise and calculable amount, and the books balance, and the second law holds after all. The units are where it turns strange. Everything else that has entropy has it in proportion to volume. Double the size of a box of gas, and you double the arrangements available, because the arrangements live throughout the box, in all 3 dimensions of it. A black hole does not work this way. Its capacity for hidden information is fixed by its surface, measured in square meters, and the interior contributes nothing whatsoever to the count. Whatever a black hole knows, it keeps on its skin. The quantities involved are not modest either. A star like our Sun, treated as a thermodynamic object with all its churning and mixing and radiating, already carries an enormous amount of entropy. Collapse that same star and the number rises by roughly 19 orders of magnitude, 10 million trillion times what it had, and nothing was added to it. No matter came in from outside, no energy was supplied. The star simply fell into a different shape, and in falling acquired more hidden information than everything it had been in the 10 billion years before. The proposal was published in 1972 and again in fuller form the year after. The reception was poor. The cleanest objection came fastest from the physicist whose theorem Bekenstein had borrowed to build the argument. If a black hole has entropy, then it must also have a temperature, because that is how thermodynamics is wired together. Anything with a temperature radiates, and an object that radiates is not black, and is therefore not a black hole. The idea appeared to refute itself on the second step, and Hawking said so. Bekenstein had rescued the second law and left something far stranger lying in plain view. His entire argument only holds if information is a physical quantity. if a count of arrangements, a measure of what has stopped being knowable, belongs in the same ledger as mass and heat and energy and can be traded against them. That is an extraordinary thing to assert, and in 1973 nobody had checked it, which leaves a question that sounds almost childish until you attempt to answer it. What does it cost to forget something? Not as a figure of speech, in joules. It turned out to be a measurable quantity, and it took another 39 years and a single microscopic bead suspended in water before anybody managed to put a number on it. You have deleted things. Everybody has. A photograph, a draft, a message thought better of, a file whose name you no longer remember on a machine you no longer own. Every one of those acts had a price, and the price was paid in heat, and it was not optional. It didn't depend on the software or the storage medium or how carefully the engineering had been done. There is a flaw beneath the cost of forgetting. The flaw is not zero, and no technology that will ever be built anywhere in this universe can get underneath it. The claim belongs to Rolf Landauer, who made it in 1961 while working at IBM. And the surprising part is not the existence of the price, but where it falls. Computing, Landauer argued, is free, not free in practice. Real machines run hot for a dozen mundane engineering reasons, but free in principle, with no thermodynamic minimum attached to it at all. You can add, multiply, compare and sort without any lower bound on the energy required, provided you do it in a way that keeps the inputs recoverable from the outputs. The arithmetic costs nothing. What costs is throwing away the working. Any operation that destroys the ability to reconstruct what came before must dissipate energy into its surroundings, and Landauer worked out the minimum. It is a fixed quantity per bit, set by the temperature of the environment and by nothing else whatsoever. Not by the design, not by the material, not by what the bit happened to mean. The reasoning comes straight out of the accounting Bekenstein would use 11 years later on a much larger object. A memory holding one bit has two states available to it. After erasure, it has one, because that is what erasure means. Whatever it was storing, it now reads the same. The number of arrangements available to that memory has halved, so its entropy has fallen. And entropy is not permitted to fall. The shortfall has to be made up somewhere outside the device, and the only currency available for the transaction is heat leaving into the surroundings. The universe does not object to you forgetting. It simply requires you to warm the room by a specific amount while you do it. The name Bekenstein chose for Wheeler's scheme was not an accident, because demons have a long history in thermodynamics and they all descend from the same one. In 1867, James Clerk Maxwell imagined a very small being stationed at a trapdoor between two boxes of gas. The being watches molecules approach and opens the door selectively. Fast ones through in one direction, slow ones in the other. No work is done. The door is frictionless, and the being merely decides. After a while, one box is hot, the other is cold. A temperature difference has appeared out of nothing at all, and the second law has been broken by something whose only activity was paying attention. That puzzle sat open for well over a century, and the early attempts to close it all went after the measurement. The demon must spend energy to see the molecules, the argument ran, and that expenditure settles the debt. It's a reasonable thought, and it happens to be wrong. In 1973, Charles Bennett demonstrated that measurement can in principle be performed at no thermodynamic cost whatsoever. The demon can look for free, indefinitely, and nothing in physics stops it. What the demon cannot do for free is forget. It has a memory, the memory fills up, and eventually it has to be cleared so the work can continue. Bennett published the resolution in 1982, and Landauer's principle does all of the lifting. The entropy the demon appears to be removing from the gas is exactly the entropy it is obliged to dump into the room when it wipes its own records. The demon has stolen nothing. It has been running a debt the entire time, and the debt falls due at the moment of erasure, which is the same shape of argument that had already been made at Princeton, arrived at independently and from the opposite end of the scale. Wheeler's demon doesn't remove entropy from the universe either. It relocates it somewhere nobody had thought to check. Landauer's principle went unmeasured for 51 years, and the reason is unglamorous. The quantity involved is absurdly small. Every real computer that has ever been built dissipates thousands of times more heat per operation than the bound requires, purely as waste, for reasons that have nothing to do with information at all: resistance, leakage, the ordinary inefficiency of pushing electrons through silicon. The signal was buried under the noise by several orders of magnitude. Erase every bit of storage in your house simultaneously, and the heat you'd be obliged to release by this principle alone would not raise the temperature of the air by any amount an instrument could find. To see the flaw, somebody had to build a memory with exactly one bit in it and nothing else going on. The apparatus that finally did it sits on a bench in a laboratory in Lyon. 2 laser beams, focused down and held a short distance apart, make 2 shallow pits in a small volume of water, places where a transparent object will settle and stay because the light pushes it toward the brightest point. Between the pits there is a ridge. A single glass bead, far too small to see without a good microscope, rests in one pit or the other. And which pit it rests in is the bit, left or right, 0 or 1. Nothing else about the bead carries any meaning. Erasing it is a matter of geometry, and the elegance of it is that you can watch the whole thing happen. Lower the ridge until the bead can wander across. Tilt the arrangement gently toward the left-hand pit and hold it there until the bead has certainly arrived. Raise the ridge again. Whatever the bead was doing beforehand, it is now on the left, and no measurement made afterward could recover where it started. The bit is gone. That is what erasure is, stripped of every convenience and every layer of engineering, a physical process whose ending does not depend on its beginning. They tracked the bead continuously, thousands of times a second, and from the record of where it traveled and how firmly the light was pulling on it, they could calculate the work done on it and the heat that went out into the water. Then they ran it again and again, hundreds of cycles, because a single bead suspended in liquid is a noisy object, and the quantity being hunted is small enough to disappear into that noise unless you average it patiently away. The result matched Landauer, and the paper appeared in Nature in 2012 under a title that does not hedge at all: Experimental Verification of the Principle Linking Information and Thermodynamics. The body of it is more careful than the title, and the condition it carries is the part that tends to fall out of retellings. What they demonstrated is that the dissipated heat approaches the Landauer bound in the limit of long erasure cycles. Slow the process down and the cost falls toward the floor. Speed it up and it climbs. The theoretical minimum price of forgetting, the one that cannot be beaten by any means, is only available to something prepared to take an infinite amount of time about it. Everything that forgets quickly pays a premium, and the faster it forgets, the more it pays. So the accounting runs all the way down and all the way up. The universe charges for forgetting at every scale anyone has managed to check. One glass bead in a laser trap in a basement and a horizon wider than a solar system, obeying a rule that turns out to be the same rule. A black hole, on this reading, is simply the largest erasure operation the laws of physics allow. Everything crossing the boundary stops being distinguishable from everything else that crossed, and the bill arrives as an increase in the horizon's area, precisely as the books require. Bekenstein's ledger balances. It balances elegantly, and it goes on balancing right up until somebody asks the obvious follow-up, which is what becomes of the account when the black hole itself is no longer there to hold it. Nobody was asking that in 1973. The proposal was still being treated as an interesting mistake, and the person best equipped to expose the mistake had already started work. In Cambridge, a physicist in his early 30s who had spent the previous decade proving theorems about what black holes must and must not do, had decided to settle the business properly and had begun a calculation designed to show that the entropy of a black hole was a coincidence of the mathematics and nothing more. It took him the better part of a year. The answer he got was not the one he had gone looking for, and it turned out to be correct. The Rutherford Laboratory sits in open country at Chiltern in Oxfordshire, a government science site of low buildings and wide car parks with fields on every side. On the 15th and 16th of February 1974, it hosted the second in a series of conferences on quantum gravity, perhaps 100 physicists, rows of chairs, a screen at the front. Outside, the country was rationing electricity. Britain had been on a 3-day week since the 1st of January, industry limited to 3 days of power, and the television stations going dark at 10:30 each night, and it would stay that way until March. Hawking was 32, 11 years past a diagnosis that had given him 2. The wheelchair by then was permanent. His voice was still his own, but it had begun to slur and thicken, and people who didn't know him well had to lean forward and work at the sound to get the words out of it. The room leant forward and worked at it. What he had come to say took a few minutes to deliver and about a decade to be generally accepted, and to understand why it landed the way it did, you have to know what he had been arguing the year before. Hawking is remembered now as the man who discovered that black holes glow. He had spent the previous year trying to establish that they could not, and he had put it in print. In 1973, working with James Bardeen and Brandon Carter, he had published a paper setting out 4 laws of black hole mechanics in exact parallel with the 4 laws of thermodynamics. One quantity behaving like temperature, another behaving like entropy, the whole structure lining up with a neatness that was impossible to ignore. The paper was careful to say that the neatness was formal, a resemblance in the mathematics, nothing more. And it stated plainly that the temperature of a black hole is 0, for the obvious reason that nothing comes out of one. 3 names on that paper. Within about a year, one of them had shown it was wrong. The thing that pushed him into the calculation came from Moscow. In 1973, he visited and met Yakov Zeldovich and a young colleague, Alexei Starobinsky, who had worked out that a spinning black hole ought to throw off particles, that quantum effects would let it bleed away its rotation. Hawking thought the argument was right in spirit and slack in execution, and he set out to redo it properly, with the full apparatus of quantum fields in curved space-time, expecting to tidy up the Russians' result, and in passing dispose of Bekenstein's entropy along the way. The trouble began when he set the rotation to 0 and the emission failed to switch off. Quantum field theory has no clean notion of nothing. What we call empty space is a field sitting in its lowest available state, and which state counts as lowest turns out to depend on the observer, on how they are moving, and on the shape of the space-time they are moving through. 2 observers in the same region can disagree, both legitimately, about whether there are particles in it. In flat and unchanging space, this never causes difficulty because everybody agrees. Collapse a star, and space stops being flat and stops being unchanging, and the emptiness that existed before the collapse is not the same emptiness that exists after it. The mismatch between them is not a bookkeeping error. It comes out as particles streaming away from just above the horizon indefinitely. The picture most people carry around, a pair of particles flickering into existence at the boundary, one falling in and one escaping, arrived much later from Hawking's own popular writing in the 1980s. It has been enormously useful, and it is not what the mathematics says. Nobody has ever managed to build a working local description of the effect along those lines. It's a story told about the calculation rather than a reading of it. He checked it for months, convinced he had made an error somewhere, and the answer kept coming back the same. The spectrum was thermal, a clean black body spectrum, the signature of an ordinary hot object at a temperature proportional to exactly the quantity Bekenstein's entropy had required. So on the second day at Chiltern, he told a room full of relativists that black holes are not black. John Taylor of King's College London was not persuaded, and the line that came down from that room is remembered because of where it was said and how little it was softened. Sorry, Stephen, but this is absolute rubbish. The exact wording reaches us through retelling and ought to be held the way all such lines are held. What is not anecdotal is what Taylor did afterward. 5 months later, he published a formal rebuttal in Nature, written with Paul Davies under a title that took Hawking's own question mark and turned it back on him. Do black holes really explode? The disagreement is in the literature, in print, with a date on it. Nobody constructed it later for the sake of a good story. Hawking's own paper had appeared in Nature on the 1st of March, 2 weeks after the conference, and it is worth noticing that his title carried a question mark too. Black hole explosions? He had spent the better part of a year satisfying himself the result was real, and he still put it out as a question. The temperature that falls out of the calculation depends on one property and one only, which is the mass, and it runs backwards from every intuition anyone brings to it. Larger black holes are colder. The monsters at the centers of galaxies are colder than the small ones, and the small ones are colder than anything you can readily imagine. For a black hole with the mass of our Sun, the temperature is about 62 billionths of a degree above absolute zero. The cosmic microwave background, the leftover warmth of the early universe, is the coldest thing that fills space, the temperature you find everywhere once you are far enough from anything that shines. It sits a little under 3 degrees above absolute zero. A black hole with the mass of the Sun is roughly 44 million times colder than the coldest background the universe provides, and the power involved is where the imagination gives out entirely. It radiates at around 100 billionths of a watt. One living cell in your body, running its ordinary metabolism, puts out something like 10,000 trillion times more than that. And because the temperature runs inversely with the mass, the process has an unpleasant shape to it. Every particle that escapes carries a little mass away, and a slightly lighter black hole is a slightly hotter one, which radiates slightly faster, which lightens it further. Whatever else this is, it does not taper off gently toward the end. It runs away, faster and hotter all the way down. There is no reference point available for cold like that. You have never been cold. The coldest you have ever been, on the worst night of your life, sat within a few tens of degrees of the temperature of the room you are in now, and every refrigerator ever built and every glass of iced water anyone has ever poured occupies a band so narrow against the range of the possible that it barely registers as a distinction at all. The object radiating at 62 billionths of a degree is not cold in any sense you have a body for. It is giving away everything it contains, quietly, at a rate too small to name, and it will go on doing so for longer than the universe has so far existed by a margin that has no useful comparison. He had found the radiation. What he had not yet done, what nobody had thought to do, because the result itself was still being argued over, was look carefully at what the radiation was made of. When Hawking finally looked closely at what was coming off a black hole, the answer was that it was entirely ordinary, and the ordinariness turned out to be the catastrophe. The radiation was thermal a technical word carrying very precise content and almost no drama, and it produced the most destructive result anywhere in this story. Any object with a temperature glows. A poker left in a fire, the filament in a bulb, your own body throwing infrared into a cold room. All the same phenomenon, and the shape of the glow follows a curve worked out by Max Planck at the turn of the 20th century. That curve has exactly one adjustable parameter. Give me the temperature and I can draw the whole spectrum for you. How much light at every wavelength, to any precision you like, with nothing left over to specify. A perfectly thermal spectrum is a spectrum carrying one number and no others, which by itself proves nothing, and this is where most retellings go quietly wrong. Ordinary hot things emit thermal radiation too, and nobody believes a bonfire destroys anything. The reason is that the spectrum is not where the information lives. Consider a stream of radio noise, genuine noise, the atmospheric hiss between stations, set beside an encrypted transmission. Examined the same way, they are indistinguishable. Same flat statistics, same absence of any pattern you could name, same refusal to resolve into anything. The difference between them does not appear in any single measurement. It lives in the correlations, in the relationships between one part of the signal and the next, which in the encrypted stream carry a message, and in the noise carry nothing, because there is nothing there to carry. Light coming off a burning object behaves the same way. The spectrum gives you the temperature, and that is all it gives you. Everything about what is actually burning survives in the fine correlations between one emitted photon and the next, statistical relationships far below the reach of any instrument anyone will ever build, and, as far as physics is concerned, entirely real and entirely present. What Hawking's calculation produced was a spectrum indistinguishable from any other thermal spectrum and correlations of exactly zero. Each quantum leaving the horizon arrived independent of every other one. Not correlated too weakly to detect, not correlated in ways requiring some future technology to unpick. Uncorrelated by construction, as a direct consequence of the mathematics, with nothing hiding in the fine structure, because the calculation left no fine structure to hide in. So two black holes of the same mass emit the same radiation, not similar radiation, and not radiation differing in ways too small to measure, the same quantum for quantum, identical in every property the theory allows you to ask about. One of them might have formed from a collapsing star. The other, if you like, from every book ever printed, fed in slowly across a few million years. The output is the same output, the entire written record of a species, reduced without residue to a temperature reading. Hawking published the consequence in 1976 in a paper titled Breakdown of Predictability in Gravitational Collapse, and to see what he was claiming, you need one distinction from quantum mechanics. The theory sorts the states a system can occupy into two kinds. A pure state is one where everything knowable is known, no missing fact, no hidden variable, nothing withheld. A mixed state is genuine ignorance, a spread of possibilities with probabilities attached and no answer underneath. And quantum mechanics has one utterly rigid rule about traffic between them, which is that pure states evolve into pure states without exception. Systems appear to go mixed constantly. A gas settles into equilibrium, a signal dissolves into hiss, a hot cup meets a cold one. In every case, the purity has only relocated into correlations with the surroundings, and the total is exactly as pure as it started. The theory contains no mechanism whatsoever for making the conversion real. Hawking's argument was that black hole evaporation makes it real. Begin with a star or a library in a definite quantum state. End with a cloud of thermal radiation and no black hole, and that radiation is genuinely mixed, not mixed relative to correlations you failed to keep track of, because the calculation says there are no correlations. pure has gone to mixed, permanently, with nothing anywhere holding the difference. He was thorough about it. He proposed replacing the standard machinery of quantum mechanics with a modified operation that maps the one kind of state to the other and gave it a symbol, a capital S with an extra stroke through it, which everybody immediately started reading as a dollar sign. It has been called the dollar matrix ever since. New notation, invented for the specific purpose of describing the universe losing track of itself. There is a promise buried in the structure of physics that almost nobody notices, because until 1976, nothing had come near breaking it. Every fundamental law we have runs equally well in both directions. Given the complete state of a closed system now, the equations reconstruct the state at any earlier moment, exactly, without ambiguity. Which means that in the ordinary course of things, the past is still here. Every conversation you have ever had is encoded at this moment in the light that left the room, the air that carried the sound, the small quantity of warmth your body contributed to it, dispersed across a volume that keeps expanding in a form nothing will ever reassemble, and present. You will never get any of it back, and that was never the point. The point was that it remained. The universe does not maintain an archive out of any interest in the contents. It maintains one because the equations have no facility for forgetting. If the 1976 paper was right, they acquired one. The promise turns out to have an exception, and when that exception runs to completion, the earlier state is not merely beyond reach. Nothing existing afterward is sufficient to specify it. The past stops being implied by the present. I keep returning to whether destroyed is the right word, and I have come to think it isn't. Destruction implies an event, a moment when a thing was whole, a later moment when it wasn't, and some mechanism operating in between. None of that applies. There is no instant at which the information gets wrecked. It isn't shredded at the boundary. A great many serious proposals have it sitting perfectly intact inside for an extraordinarily long time. It isn't burned or diluted or torn up. What happens is that the black hole finishes, and afterward nothing in the universe specifies what went into it, and nothing ever will again. The information is not destroyed at a particular time. It simply fails to be anywhere from then onward. Lost is worse, since lost implies findable. Erased implies an eraser. Forgotten implies something that used to remember. English has no word for this, and the reason is uncomplicated enough. Nothing in ordinary experience does it, and as far as anyone knew, nothing in physics did either. It's worth registering whose conclusion this was. 2 years before, he had found something extraordinary, been told in front of a room that it was rubbish, and turned out to be right. Then he took his own discovery, followed it honestly to the end, and came back to report that it broke quantum mechanics. He did not offer this as a difficulty awaiting resolution. He offered it as a result. His position was that the theory would have to yield, which leaves a question, and it isn't the one you would expect. Where the book went stops being the interesting problem. If the radiation carries nothing out, then something stranger is at stake much further back. What did the black hole ever know about the book to begin with? And in an object describable by 3 numbers, where could it possibly have kept it? It couldn't have kept it anywhere. That turns out to be the answer, and the reasoning behind it is considerably stranger than the bare fact. The 3 numbers are not a limitation of our instruments, and they are not a statement about how far away the nearest black hole happens to be. They are a theorem. Somebody proved it across roughly 8 years of work by several people, and the proof is what makes it unsettling rather than merely inconvenient. General relativity is an extravagantly generous theory. Ask it to describe a star, and it hands you an infinity of answers. Every possible distribution of matter, every lumpy and irregular configuration, every star that has ever existed and every one that never will, each of them a distinct object with a distinct and detailed description. The equations place almost no restriction on what a quantity of matter is permitted to look like. Ask the same theory about a black hole, and the generosity stops dead. Werner Israel demonstrated in 1967 that a static one admits exactly one possible form. Brandon Carter narrowed the rotating case in 1971 to a single family. Hawking proved that a stationary black hole must be symmetric about its axis, and David Robinson closed the argument in 1975. Taken together, they established that the entire space of possible black holes has 3 dimensions to it. Not approximately 3, pending further refinement. 3 parameters, and every black hole that exists anywhere is one point in that space. Why it should be 3 rather than 4 or 100 or none has an answer, and it arrived in the article that gave the whole idea its name, a piece by Remo Ruffini and John Wheeler in Physics Today in 1971 called Introducing the Black Hole. The quantities that survive are precisely the ones with a reach. Mass has gravity attached to it. The mass of an object is felt at a distance. A field extends outward from it into the surrounding space, and that field is still there once the object has gone behind a horizon. Electric charge carries electromagnetism and does the same. Rotation twists the space around it in a way that can be measured from outside. This has actually been done in Earth orbit by satellites carrying gyroscopes and watching them slowly lean. Everything else about a quantity of matter is a fact about its interior. What it is made of, how it is arranged, how many protons are in it, what it used to be. None of these announce themselves at any distance at all. There is no field that a book produces by virtue of being a book. So when the boundary closes over, those facts have no channel through which to be known and no channel through which to persist. A black hole is not concealing the contents. It has no organ for reporting them, and the theorem says there is nothing left over that concealment would even apply to. Some of what goes down with the ship was not supposed to be expendable. Baryon number is the clearest case. Protons and neutrons are baryons, you can count them, and that count is conserved by every process anyone has ever seen, not approximately conserved, but conserved with a strictness that has been hunted for decades and never once caught slipping. There is a detector in a zinc mine in Japan, a kilometer below the surface, holding 50,000 tons of ultra-pure water inside a shell of 11,000 light sensors, and one of the things it exists to do is watch for a single proton coming apart. If protons decay at all, the flash is unmistakable. It has been watching for 30 years and has never seen one, which puts the lifetime of a proton somewhere above 10 to the 34th years, longer than the present age of the universe by around 24 orders of magnitude, a limit established entirely by patience. Take that same proton and drop it past a horizon, and the count goes down by 1 at once, with nothing offered in exchange. Lepton number goes the same way. So does strangeness, and every other quantity physics keeps a ledger for. The conservation laws that survive 30 years of the most careful watching anyone has ever arranged do not survive a boundary. And here the two halves of this story fail to fit together in a way that has never been repaired. The theorem says a black hole has no internal structure accessible to the outside, 3 numbers and nothing underneath them. Bekenstein's entropy says it has more internal structure than any other object in existence. Both of those are current, mainstream, load-bearing physics, and they are describing the same thing. Entropy is a count of arrangements. An entropy of a given size means a specific number of distinct internal configurations, every one of which looks identical from where you are standing. So the claim sitting on the table is that a black hole possesses an astronomical quantity of distinguishable internal states, together with a complete external description consisting of 3 numbers. On the present accounting, It is the simplest object in the universe and the most complicated one simultaneously, and working out how to hold both of those at once has occupied a great many careers. The scale of the mismatch is where this stops being an abstract difficulty. At the center of our galaxy, there is a black hole called Sagittarius A star, a little over 4 million times the mass of the Sun, and its horizon covers an area of roughly 2,000 billion square meters. Run the accounting across that surface, and it comes to something close to 10 to the 90th bits. The number of distinct internal states corresponding to that is 2 raised to that power, and this is the point at which language gives out. Writing the figure down in full would take something like 10 to the 90th digits. There are around 10 to the 80th atoms in the observable universe. Assign 1 digit to every atom and you exhaust the atoms roughly 10 billion times over before finishing. And that is only the number that counts the states, not the states themselves. Widen the frame all the way out. Add up the entropy of everything in the observable universe, every star, all the gas drifting between them, the leftover heat of the beginning that fills every cubic meter of space, and then add the black holes, and the black holes swamp the rest so completely that everything else becomes a rounding error. The best current estimate for the total sits near 10 to the 104th, and the supermassive black holes account for very nearly all of it. Stellar mass black holes on their own carry 17 orders of magnitude more entropy than every star that has ever shone. The cosmic microwave background, the next largest contributor after the black holes, comes in about 16 orders of magnitude below the total. For something with a human scale attached, the entire digital collection of the Library of Congress runs to roughly 20 petabytes. That single object at the center of our own galaxy has an information capacity around 10 to the 73rd times larger, which leaves you in a peculiar position, and it's worth being exact about the peculiarity. Everything you have ever seen, every star, every galaxy, in every photograph anyone has taken, all the light that has ever arrived at this planet from anywhere, comes from the portion of the universe that still radiates. That portion is the residue. The overwhelming majority of the universe's information content is already behind horizons, held in objects that will not report it and cannot be asked, and has been for a very long time. You are living in the thin-lit skin of something much darker and much fuller. There is a difference between a number that is large and a number that is large in a way that defeats the equipment you are using to think about it, and everything in the last few minutes belongs firmly to the second kind. I don't believe there is much to gain from trying to feel them. The honest procedure is to note the figure, satisfy yourself that it's correct, and set it down carefully. 3 numbers is what the outside gets, while the black hole is there. Everything else, whatever those 10 to the 90th bits are actually keeping a record of, is either coming back later or not coming back at all. And that is the whole of the question. If it comes back in the radiation, spread across the evaporation. So finding out means waiting for the evaporation. And the waiting is where these numbers stop being merely large and turn into something with a different quality altogether. There is a detail about the evaporation that almost never survives into the popular telling, and it reorganizes everything that comes after it. The process has not started, not anywhere, not in a single case. There is no black hole in the observable universe that has so far lost so much as a gram to Hawking radiation, and none of them will for an extremely long time. The reason is arithmetic between 2 temperatures, and both figures are already on the table. Space is not cold. Space has a temperature. The leftover warmth of the early universe, stretched out by nearly 14 billion years of expansion until it sits a little under 3 degrees above absolute zero, filling every cubic meter of the cosmos with a faint uniform bath of microwaves. Nothing is exempt. Every object anywhere sits in that bath and trades energy with it. A black hole with the mass of the Sun radiates at 62 billionths of a degree, and anything larger is colder still. The bath is warmer than the black hole by a factor of tens of millions. So energy flows in the direction energy always flows, from the warmer thing toward the cooler one, and the black hole takes in vastly more than it gives out. It grows. Every black hole anyone has ever observed is gaining mass at this moment. The one at the center of our galaxy is gaining. The two that spiraled together in 2015 and rang the detectors in Louisiana and Washington were both gaining beforehand, and the object they merged into is gaining now. Every dark center in every image the Event Horizon Telescope has produced is a little heavier than it was on the day the photograph was taken. There is a threshold where the balance tips, and it sits remarkably low. For a black hole to run hotter than the background, to lose more than it collects, it has to weigh less than about 3/5 of the Moon. Take the actual Moon, compress it until it becomes a black hole, and you would have an object with a radius of roughly 1/10 of a millimeter that was still colder than empty space and still quietly putting on weight. Nothing that light is known to exist. The lightest black holes anyone has confirmed run to several times the mass of the Sun, which places them 8 orders of magnitude on the wrong side of the line. The background will cool eventually, because the universe is expanding and expansion stretches wavelengths, and a stretched wavelength is a lower temperature. Under dark energy, that expansion is accelerating, so the cooling is exponential and it does not stop. Work out when the background finally drops below the temperature of a black hole with the mass of the Sun, and the answer is somewhere near 300 billion years from now. For Sagittarius A star, colder by a factor of 4 million, the weight runs to something like 500 billion. The universe is presently 13.8 billion years old. So the interval before the first black hole anywhere begins to shrink is roughly 20 times longer than everything that has happened so far. Every star that has formed and died, every galaxy that has assembled, the whole of chemistry and geology and biology and recorded history, all of it fits inside about 5% of the run-up to the starting gun. And that is only the starting gun. Once a black hole with the mass of the Sun does begin to shrink, the shrinking takes around 2 times 10 to the 67th years. Sagittarius A star, 4 million times heavier and evaporating on a schedule that scales with the cube of the mass, needs something close to 10 to the 87th. Folded inside that, there is one further delay, and it may be the one that matters most. If the information does come out in the radiation, it does not come out evenly, distributed from the first photon to the last. There is a good argument, turning on how the correlations accumulate, that essentially nothing emerges until the black hole has already radiated away about half of everything it holds. The first 2/3 of the evaporation by duration is noise. For a black hole with the mass of the Sun, the first genuinely informative photon leaves somewhere past the 10 to the 67th year mark, after the object has spent longer than any number you have a use for giving away nothing at all. To get a feel for what that does to the idea of waiting, it helps to know the longest message human beings have seriously attempted to send. In the desert of southeastern New Mexico, there is a repository for radioactive waste, buried about 600 meters down in a bed of salt, and the regulations governing the site require that it stay marked and understood for 10,000 years. That requirement produced one of the odder pieces of engineering anyone has undertaken. Panels were convened in the early 90s. Linguists, anthropologists, materials scientists, a science fiction writer or two, and asked how you communicate danger to people who will speak no language currently spoken, who will have no reason to trust any institution currently standing, and who may not read. The proposals ran to vast earthworks, fields of concrete spikes, granite slabs carved with the same warning in 7 languages on the explicit assumption that all 7 will be dead by the time anyone arrives. 10,000 years is our outer limit. It is the furthest anybody has attempted to throw a sentence forward. The message coming out of a black hole, if it is coming out at all, needs 10 to the 67th years to finish arriving. It exceeds our most ambitious attempt at permanence by a factor of 10 to the 63rd, which would settle the observational question entirely, except for one loophole, and people have been sitting in that loophole with instruments pointed upward since the 1970s. Everything above assumes black holes form the way we have seen them form, out of collapsing stars, which puts a hard floor under how light they can be. Nothing in principle required the early universe to respect that flaw. In the first fraction of a second after the beginning, the density was high enough that an ordinary fluctuation could have collapsed directly at any mass at all, including masses far below anything a star could ever produce. Whether this actually happened, nobody knows. If it did, the objects are called primordial black holes, and some of them would be small enough to be genuinely hot. One mass in particular matters. A black hole of about 500 million tons, a block of rock half a kilometre on a side, squeezed into a volume smaller than a proton, formed at the beginning would have spent the entire history of the universe evaporating and would be arriving at the end of it right about now. The end is not gentle. Since the thing runs hotter as it grows lighter, the last stage is a runaway. The final seconds dump everything remaining in a burst of high-energy gamma rays with a distinctive rising signature that nothing else in astrophysics produces. You would know it if you saw it. 3 major instruments have been watching for exactly that. The Fermi Gamma Ray Space Telescope has been in orbit since 2008, surveying the entire sky every 3 hours. On a volcano in Mexico, 4,000 meters up, 300 tanks of water sit waiting to catch the particle showers such a burst would set off in the atmosphere. And in the Comus Highland of Namibia, an array of telescopes watches the southern sky for the same faint blue flash. Between them, they have been looking for decades. None of them has ever seen it. Not one evaporating black hole in any direction, at any time, ever. What the searches produce instead are limits, upper bounds on how many of these events can be occurring in our neighborhood each year, tightening steadily as the years accumulate and nothing arrives. That is a genuine scientific result, and it is also, if you hold it for a moment, an unusual thing to have spent half a century on. A slowly improving measurement of an event that has never once happened anywhere anybody could see it. So the answer is not coming from observation. The instruments are pointed, the sky is empty, and the process that would settle the matter does not begin for 300 billion years and does not conclude for 10 to the 67th. Whatever gets decided about this gets decided on paper, which sharpens the question into something surprisingly specific. Nobody can watch the information come out. If it were coming out, though, it would have to leave a mark somewhere in the radiation, some measurable quantity that behaves one way when information is escaping and a visibly different way when it isn't. So what does that mark look like? Somebody worked it out in 1993, and the answer is a shape. There are 2 curves. Both are drawn from the same starting conditions, using physics that nobody disputes, and both describe the same quantity across the same stretch of time. One of them rises and goes on rising. The other rises, turns over, and comes back down to nothing. They cannot both be correct, and the whole of the past 50 years is an argument about which one is. The person who drew the second curve had been Hawking's student. Don Page arrived in Cambridge as a postdoctoral researcher in the mid-1970s, at the point when the radiation result was still raw and still being contested. He worked directly with Hawking, published with him, and for a period lived in the Hawking family home, which in practice meant taking a share of the daily care of a body that was failing steadily while the mind attached to it went on producing results. He moved afterward to the University of Alberta, where he has been ever since. So when the sharpest challenge to Hawking's conclusion finally arrived in 1993, it came from somebody who had spent years living in his house. The quantity page was tracking has a name that sounds forbidding and a meaning that isn't. Entanglement entropy is a number you attach to a part of a system rather than to the whole of it, to a piece you have decided to examine on its own. Take two objects whose quantum states are bound together and suppose the pair as a whole is pure, meaning there is nothing about the pair left undetermined. Cover one of them and look only at the other. What you find is that the object in front of you is not in a definite state at all. It comes out mixed, genuinely uncertain, with real probabilities and no hidden answer underneath them, and the reason is that its state was never a property it possessed by itself. The state belonged to the pair. Entanglement entropy counts how much of that there is, how much you fail to know about the thing in your hands after measuring every property it has, because the answers were never stored in the object. They were stored in a relationship. Now apply that to an evaporating black hole. Divide the world into two pieces, the radiation that has escaped so far and the black hole still remaining, and follow the entanglement entropy of the radiation as the process runs. At the outset, it is zero because there is no radiation. Photons begin to leave, each one correlated with something still inside, and the number climbs. The disagreement is entirely about the ending. If Hawking's calculation holds and the radiation is truly thermal and carries nothing, the number climbs the whole way and simply stops wherever it stands at the moment the black hole disappears. What remains is a cloud of radiation in a mixed state, entangled with a partner that no longer exists anywhere. Quantum mechanics has no language for that situation at all. If information escapes, the ending is forced, and the requirement is absolute rather than approximate. At the end, there is only radiation. Nothing else survives for it to be correlated with. And a complete system in a pure state has an entanglement entropy of exactly zero. Nothing left over, nothing concealed in a relationship, no missing fact anywhere in it. So whatever the curve does in the middle, it has to come back to the floor. Page's contribution was to work out where the turn has to happen, and the argument runs on a ceiling. The entanglement entropy of the radiation cannot exceed the capacity of the thing it is entangled with. That isn't a physical assumption anyone had to argue for. It falls straight out of the definitions. Two systems can only share as much correlation as the smaller of them has room to hold. Early in the evaporation, the smaller party is the radiation. Very little has escaped, so the ceiling sits low and it lifts gradually as more photons accumulate. The number rises along underneath it. Late in the evaporation, the smaller party is the black hole. It has been shrinking the entire time, and its entropy, the quantity Bekenstein proposed and Hawking confirmed set by the area of the horizon, is falling towards zero. The ceiling is now coming down. Two ceilings, one rising and one descending. They cross somewhere near the middle of the process, and past the crossing, the entanglement entropy of the radiation is capped by a number heading rapidly for nothing. It has no choice but to follow it down. That crossing is what everyone now calls the Page time, and Hawking's curve goes straight through it without slowing. Past the halfway mark, the semi-classical calculation is asserting that the radiation is more strongly entangled with the black hole than the black hole has the capacity to be entangled with anything whatsoever. A violation of a bound that follows from an entropy Hawking had helped establish himself. It's worth being precise about what Page claimed, because the result gets repeated more loosely than he wrote it. He published two short papers in 1993 in the same journal, a few months apart. The first contains no black holes at all. It is a piece of mathematics about random quantum states, establishing what the typical entanglement entropy looks like when a large system is divided into two unequal pieces. The second applies that result to evaporation, and the second is conditional, from beginning to end. Page did not demonstrate that information escapes. He assumed it, took unitarity as given, treated the black hole and its radiation together as a random pure state, and worked out what had to follow. The output is the shape the curve must have if the information is coming out. A consistency requirement, not a mechanism. He offered no account whatsoever of how a photon leaving the horizon could carry a correlation that Hawking's calculation said it did not have, and he did not pretend to. What he had produced was a target, something specific, quantitative and unambiguous, that any correct theory of evaporation would be obliged to reproduce, and which the existing theory conspicuously failed to. It went unreproduced for 26 years. That is the part of this story that is easiest to underestimate. The curve is not an exotic or delicate requirement. It follows from taking quantum mechanics seriously and doing arithmetic carefully. By the late 1990s, most physicists working on the problem believed information escapes, which means most of them believed the line had to bend. Nobody could make it bend. You could write down the semi-classical calculation, the one Hawking had done, that everyone had checked and rechecked. And it produced a line that rose forever, and no amount of care in the execution altered the outcome. The attempts were serious, sustained, and made by people who were very good at this, and the answer kept coming back the same shape. So carry the picture, because everything after this is an argument about it. A quantity beginning at nothing, rising as the radiation gathers, steadily, patiently, across an interval longer than you have any means of holding in your head. Somewhere past the middle, it stops rising. And then, if this is the kind of universe that keeps its records, it descends slowly, arriving at exactly zero in the moment the last of the black hole goes. You will not see this. Nothing will. For a black hole with the mass of the Sun, the bend falls roughly 10 to the 67th years into a process that does not begin for another 300 billion in a cosmos with no stars left in it and nothing remaining that could be called an observer. The entire dispute concerns the shape of a line that no eye will ever be present for. It is also, by fairly broad agreement, the sharpest open question in fundamental physics, the one place where the two great theories of the 20th century are known to contradict one another at a specific point, about a specific number, with no room left for anyone to be misunderstanding the other. Page published in 1993. It took 11 years for the man whose calculation that curve contradicted to stand up in a lecture hall in Dublin in front of a bank of cameras and say out loud that he had been wrong. The 17th International Conference on General Relativity and Gravitation ran for 6 days in Dublin in July of 2004, and it was supposed to be a technical meeting. Several hundred specialists, parallel sessions, the ordinary business of a field talking to itself. Some weeks beforehand, Hawking had written to the organisers asking for a slot. He said he had solved the black hole information paradox and would like to present the solution. By the morning of the 21st, you could not get into the room. They had moved him to the largest hall the venue had, and it was not large enough. People who had come for the conference were standing along the walls and sitting in the aisles, and at the back there was a bank of television cameras with their lights on, sent by broadcasters who had flown in for a physics lecture. He spoke through the synthesizer, at the pace the synthesizer allowed, which is slower than any talk in that room had ever been delivered, and which had the effect of making each sentence land like a decision that had been taken some time ago. What he told them was that he had been wrong for close to 30 years. Information is not destroyed, it comes back out. He also told them, and this is the line that travelled furthest that week, that he was sorry to disappoint science fiction fans, because if information is preserved, then black holes are not doorways into other universes, and whatever goes in stays in this one. Then he settled the bet. Total Baseball. The ultimate baseball encyclopedia runs to well over 2,000 pages and is not a book you would hold comfortably in one hand. Preskill had chosen it, which was his right as the winner. And there is a photograph from that morning of him standing at the front of the hall with the thing raised over his head for the cameras, while Hawking sits beside him. Hawking's remark afterward was that he had given John an encyclopedia of baseball, though perhaps he should just have handed over the ashes. The argument he had come to present deserves setting out, because almost nobody reporting the story that week attempted it. Quantum gravity, in the approach Hawking had spent his career on, calculates what happens by summing over possibilities, not over the paths a particle might take, but over entire shapes that space-time itself might have, every geometry consistent with how things start and end, each one contributing its share to the total. His claim was that the sum has to contain two different kinds of geometry. There are the ones with a black hole in them, and there are the ones in which no black hole ever forms at all, where the matter collapses and disperses, and nothing with a horizon is ever present. Both are permitted by the equations. Both belong in the sum. The geometries containing black holes reproduce his original result and lose information. The geometries without them are entirely ordinary and preserve it. And Hawking argued that as time passes, the black hole contributions fade away toward nothing, so that at late times what remains is made up wholly of the well-behaved kind. The information returns because somewhere in the sum there is always an amplitude for the black hole never having existed, and eventually that possibility is the only one still contributing. The version he gave the press was blunter. Whatever falls in comes back out, he said, in a mangled form, carrying the information about what it was, in an unrecognizable state. The paper appeared the following year, and it is short. It does not derive the shape of Page's curve. It does not explain how a photon leaving the horizon acquires a correlation with a photon that departed 1,000,000 years earlier. It identifies no mechanism whatsoever. It argues about the structure of a formal sum, concludes that the total has to come out unitary, and stops there. Relativists who had believed information was lost went on believing it. People who already thought it escaped were given no new reason to think so more firmly. The thing that had been missing before the talk was still missing afterward. Preskill's position was awkward, and he made no effort to disguise it. He took the prize because Hawking had conceded, and terms are terms, and he said plainly that he had not followed the argument well enough to be persuaded by it. The winner of a wager about whether the universe keeps records walked out of that hall with a baseball encyclopedia and no clearer idea than he had walked in with. 5 years later, the situation deteriorated, and it deteriorated in a way that shut off the most comfortable escape route anybody had. The hope that had carried a lot of people through the 1990s was modest and entirely reasonable. Hawking's calculation is an approximation. It is a leading order result, worked out on a curved background with no full theory of quantum gravity underneath it, and nobody ever thought it was exactly right. So perhaps the information leaks out in the corrections, minute deviations from perfect thermality, far too small to show up in the leading calculation, accumulating quietly across an enormous number of emitted quanta until they add up to the whole thing. In 2009, Samir Mathur proved that this cannot happen. The argument is short and rigorous, and it relies on a general property of entanglement rather than on any particular model of quantum gravity. If the correction to each emission is small, if the radiation departs from Hawking's answer by any amount you would still be willing to call a correction, then the entanglement entropy of the radiation is forced to keep climbing. Not approximately. It rises by a guaranteed minimum at every step. It never turns over, and the curve never bends. So whatever resolves this is not a small correction. It has to be a change of order 1, and it has to happen at the horizon, which is a region where nothing is supposed to be happening at all. That conclusion is most of the reason the following decade went the way it did. Whether Hawking was right to concede in that hall is, 22 years later, still not something anyone can tell you with confidence. The consensus has travelled a long way in his direction. Most people working on this now believe information escapes, and the case has strengthened considerably. But the specific argument he made in Dublin has not aged into persuasiveness. It has quietly been set aside. He arrived at what is probably the correct conclusion by a route that most of his colleagues did not accept at the time and do not accept now, and he did it in front of television cameras, having announced in advance that he was going to. I can't settle on what to make of that. It reads either as the sharpest instinct in the room or as a man who wanted very much to be finished with a problem that had taken 30 years off him. Both readings fit the available evidence, and both are entirely compatible with him having been right. Kip Thorne was in that hall. He had signed the same page in 1997 on the same side of the bet, and he did not concede. He declined to contribute to the prize. His stated reason was simple, and it anticipated Mathur's result by 5 years. Hawking had not shown any actual route by which the difficulty could be removed. He has never moved from that position. He was still explaining it publicly in late 2024, 27 years after putting his name on the page, and 7 years after collecting a Nobel Prize for the detection of 2 black holes colliding, which makes him the only figure in this story who has both argued about these objects on paper and measured one directly. The room applauded. Thorne stayed in his seat. What is an answer worth if nobody can ever check it? That sounds like a question for philosophers, and it is about to become an entirely practical one, because for 19 years the accepted resolution to this problem was a proposal whose central defense was that no experiment could ever test it. Not a difficult experiment, not one requiring instruments we haven't built. An experiment that the structure of space-time appears to have been arranged specifically to prevent. By 2004, most physicists already believed the information escapes, and none of that had anything to do with what Hawking said in Dublin. The belief had been settled for over a decade, and it rested on an idea published in the same year as Page's curve by 3 people who came at the problem from the direction of string theory. Leonard Susskind, Lars Thorlacius, and John Uglum put it out in October of 1993, building on earlier work by Gerard de Hooft, and the paper has since been cited well over 1,000 times. Its title names the 2 components, the stretched horizon and black hole complementarity. The stretched horizon is the more concrete of the 2. An event horizon is not a physical surface. It is a boundary defined by where light can and cannot get out, and there is nothing at the location itself. Yet from a distance, the region just above it behaves precisely as though something were there. Matter falling toward a black hole appears, to a distant observer, to slow as it nears the edge, because time runs slower the deeper you go. It never quite arrives, and instead spreads and flattens against the boundary and heats. An earlier generation of relativists, Kip Thorne among them, worked out that you can treat that layer as a genuine membrane with genuine physical properties, and the properties are specific. It has a temperature, it has entropy, it has a viscosity, and it conducts electricity with a surface resistance of 377 ohms, which happens to be the impedance of empty space, and is a startling figure to be able to quote about a place where nothing exists. For every purpose an outside observer will ever have, the black hole is that membrane, a hot object hovering a hair above the boundary, and hot objects absorb things and give them back. Now drop a book in and ask what becomes of it. There are 2 answers. If you stay outside and watch, the book never crosses. It slows as it approaches and reddens as its light stretches out, flattens against the membrane and thermalizes, comes apart into the hot fabric of that surface, its contents smeared across the layer. Then, across an interval nobody has a use for, the membrane radiates all of it back out. Nothing was destroyed, nothing ever went inside. If you travel with the book, none of that occurs. You cross a boundary that carries no marking of any kind, in a region where every equation says nothing unusual is happening, and you notice nothing whatsoever. The book is beside you, intact, continuing inward. There is no membrane. There was never a membrane. What an outside observer describes as a hot surface is, from where you are, an unremarkable patch of empty space you have already passed through. Both accounts are asserted to be complete and both are asserted to be correct. Not two halves of a single description, two entire descriptions of the same book, in flatly incompatible physical states. Reduced to a residue on a surface and sitting undamaged a long way past it. That is not a difference of perspective in any ordinary sense, and it is worth being exact about how severe it is. Quantum mechanics contains a theorem, proved in 1982, stating that an unknown quantum state cannot be copied. Not that copying is impractical, the operation does not exist. The linearity of the theory forbids it, and a great deal of modern physics, from quantum cryptography to the impossibility of certain kinds of faster-than-light signaling, rests on that prohibition holding absolutely. Complementarity requires the book to exist in two places at once. It is a direct violation of one of the most secure results in the subject. The escape is that nobody can ever witness the violation, and this part is not a hand wave. Somebody sat down and worked out the numbers. Catching the duplication would require a single observer who sees both copies, so the procedure would run like this. Stay outside. Collect the radiation as it comes. Once enough has emerged, past the halfway point where the correlations start becoming decodable, extract from those photons what the book said. Then jump in, carrying what you have learned, catch up with the original still falling, and compare the two. The calculation says it cannot be done. By the time you have gathered and decoded enough radiation to know anything, the interior copy is so far along that for it to get any signal to you at all, in the time remaining before there is no more interior to be in, it would have to send a photon carrying more energy than the entire black hole contains. The experiment is not merely beyond reach, it demands more energy than the object being studied has in it, which is a strange sort of victory. The contradiction is real, and the geometry of the universe has been arranged so that nobody will ever be positioned to point at it. I keep circling the question of whether that counts as a resolution. Complementarity is not obviously wrong, and it has a serious pedigree. Bohr made the identical maneuver in the 1920s about whether light is a wave or a particle, and that turned out to be one of the great clarifying moves in the history of the field. Nobody now regards both, and no experiment can reveal both as a dodge. It was simply the answer. There is a difference between the two cases, though, that I have never managed to dissolve. In Bohr's version, the two descriptions never claim that one thing exists in two locations. A photon is not asserted to be here and also over there. The black hole version asks for something considerably stronger, that a specific object with specific contents occupy two mutually exclusive physical states, with the reconciliation being that the shape of space-time prevents anybody from ever filing the complaint. I can construct the argument that this is acceptable. I have never been able to make myself believe it, and I notice that a great many physicists spent 19 years in something like the same position, using the idea, building on it, publishing with it, and not quite believing it either. It held from 1993 until 2012, and what eventually broke it was not new physics. No telescope was involved, no experiment was performed, no particle discovered, no constant measured to a further decimal place. 4 physicists sat down and checked the postulates against one another more carefully than anybody previously had, using arguments about entanglement that had been sitting available the entire time, and found that the postulates are not consistent with each other. The flaw had been inside the proposal from the day it was published. It took 19 years for anyone to look in the right place. Before that happened, though, somebody asked a narrower question, and the answer reshaped the whole discussion. Complementarity leans on the black hole mixing whatever falls in thoroughly, and quickly enough that the outside description holds together. So how quickly does it actually manage that? Not quickly in a manner of speaking, but measured against what the laws of physics allow. What came back was that a black hole does this at the maximum rate the universe permits, and that nothing, anywhere, is faster. Everything in the universe that mixes things does it at some rate. Stir milk into coffee and the pattern is unrecoverable within seconds. Drop a sealed bottle into the ocean and the water takes decades to disperse what leaks out of it. Set fire to a page and the correlations holding the words together scatter into the room at roughly the speed of the flame. There is a fastest possible rate for this. Not a technological ceiling or a practical one. It follows from how information can move through a system with a given number of parts, and no arrangement of matter anywhere is permitted to beat it. Black holes sit precisely on it. The word for what they do is scrambling, and it means something narrower than mixing. A system is scrambled when whatever you put into it can no longer be found in any small piece of it, when you could examine any modest fraction of the thing and come away with nothing, because what you deposited has been spread out into correlations between every part and every other part. How long that takes depends on how the parts communicate. In a fluid, or a gas, or anything where interactions happen by contact, information travels locally and the time scales with the size of the system. Where every part can affect every other part directly, it goes considerably faster because the spreading is exponential. 1 part infects 2, 2 infect 4, 4 infect 8, and the number of steps required to reach everything is the logarithm of the number of parts. The logarithm is the flaw. Nothing can be quicker because you cannot inform more than everything, and doubling is the fastest way to arrive. In 2008, Yasuhiro Sekino and Leonard Susskind proposed that black holes hit that bound exactly, that they are, in the phrase that stuck, fast scramblers, and that nothing in nature scrambles faster than they do. Put numbers on it for the object at the center of our own galaxy. The horizon of Sagittarius A star has a radius of about 13 million kilometers, which light crosses in roughly 42 seconds. Multiply that by the logarithm of the number of internal states available to it, and the scrambling time comes out at something close to 2.5 hours. Drop anything into Sagittarius A star, and within an afternoon it is gone in the only sense that matters, not destroyed, but distributed so completely across the horizon's degrees of freedom that no reachable portion of it retains any trace of what arrived. 2.5 hours to scramble. 10 to the 87th years to give any of it back. Which raises a question that Patrick Hayden and John Preskill asked in 2007 in a paper carrying the best title in the whole subject, Black Holes as Mirrors. The setup is easy to state. Suppose the black hole is old, past the halfway point, where the correlations have accumulated as far as they are going to. And suppose somebody now throws in something new, a page, a photograph, a single sentence. How long before it comes back out? The expected answer was something like half the remaining lifetime, on the reasonable assumption that the black hole would have to radiate away a comparable fraction of itself before anything new could be extracted from it. The actual answer is the scrambling time. An old black hole gives back what you hand it almost immediately, encoded into the next handful of photons it emits on a timescale of hours rather than eons. It behaves the way the title says, Whatever you send at it comes straight back at you, unrecognizable, and essentially at once. There is a condition attached, and it is not a modest one. The reason an old black hole can return things so quickly is that it is already thoroughly entangled with everything it emitted before. New information gets woven into that existing web and becomes readable in the next few photons out, but only to somebody who holds the web. To decode the page from the radiation arriving this afternoon, you must already possess essentially all the radiation that came out beforehand. For a black hole with the mass of the Sun, that means having collected and stored, perfectly and without loss, every photon emitted across 10 to the 67th years, over a sphere that has been expanding throughout, in a universe that stopped containing anything else a very long way back. And then you need a quantum computer large enough to process the whole collection. The information is available in roughly the way a conversation is available if you happen to have kept every molecule of air in the room. The nearest thing in ordinary life is the difference between a record being lost and a record being unreadable, and we have recently built a rather good example of the second kind. There are wallets sitting on public ledgers at this moment, holding substantial fortunes that anybody in the world can inspect and nobody can spend because the keys were thrown away. The balances are not in dispute. Anyone can verify them to the last decimal at any time they like. The ledger is complete, public, permanent, and entirely useless. And the reason is not that any information was destroyed. The reason is that the one thing required to act on it is gone. That is roughly the condition the universe may be offering here, and the distinction is worth holding on to, because the two situations are not remotely the same physics. Information destroyed breaks quantum mechanics. Information preserved and unreachable breaks nothing whatsoever. It simply doesn't help. Two different claims have been running together through this entire argument, and only one of them is genuinely in dispute. Whether the information is preserved is the 50-year question, and the answer appears to be yes, though nobody has yet proved it. Whether it can be recovered was settled some time ago, and there the answer is no. Not difficult, not awaiting some future instrument, but no, in the way that the scrambling time is a bound, and the collection requirement is a bound, for reasons built into the structure of the object, permanently, for any observer that could ever exist anywhere. So whatever you throw in is safe in an unusually specific sense. It has not gone, the universe has not forgotten it, and if the current consensus holds, the universe is incapable of forgetting it. It has only been written into a form so thoroughly distributed that reading it back would require being larger than the process that recorded it, and older and more patient than anything that will ever exist. Which is a strange thing to be able to say about an object whose entire reputation rests on destroying what it touches. All of this assumes the boundary is an ordinary place, that the horizon manages the whole operation quietly in a region where the equations insist nothing much is going on. Complementarity requires that. The mirror requires it. Every picture currently on the table depends on the horizon being unremarkable to anything that crosses it. So what is actually happening there in the moment a photon departs and its partner falls? 4 physicists in Santa Barbara set out in the summer of 2012 to answer that properly, intending to settle the last doubts about complementarity in its favor. They were defending an idea they believed in. By the end of the summer, they had taken it apart. 4 statements. Every one of them is believed by essentially everybody who works on this. Everyone has good reasons behind it, and at least 2 are more or less beyond question. They cannot all be true. Not for subtle reasons awaiting some future discovery, they are inconsistent with one another, demonstrably, using mathematics that had been sitting available since the 1990s, and the demonstration runs to about a page. You could follow it if somebody walked you through the notation. What you are about to lose, if you accept the argument, is not a technical convenience. The Kavli Institute sits on a bluff at the western edge of the University of California at Santa Barbara, close enough to the Pacific that the sound of it reaches the terrace, and the building is arranged around blackboards. In the corridors, in the offices, outdoors on the patio, the whole place organized on the assumption that its purpose is people arguing at chalk. Through the summer of 2012, 4 of them were arguing at the same one. Joseph Polchinski was a permanent member there, one of the most respected theorists of his generation. Donald Marolf was a professor in the physics department. Ahmed Almheri and James Sully were graduate students. The work had the particular texture of a calculation that refuses to come out. They would set up the situation, impose the assumptions everyone agreed on, and derive a contradiction. Then they would hunt for the mistake, find something that looked like one, correct it, and derive the contradiction again. This went on for weeks. The inequality kept coming back in the same form, arrived at from different directions, and would not be talked out of it. They were not attacking complementarity, they were defending it. The idea had sat at the center of the field for 2 decades without anybody doing the careful work of checking its postulates against one another under the conditions where they would be strained hardest. An old black hole well past the halfway point, with the correlations fully built up. The intention was to close that gap and settle the last doubts in its favor. What they kept running into turns on a property of entanglement that has no counterpart anywhere in ordinary experience. Ordinary correlation is shareable. 3 people can know the same secret, and so can 100. Write a fact down, and any number of copies can be made, held by any number of parties, and nothing in the world objects. Entanglement does not behave this way. If 2 systems are maximally entangled with each other, as strongly correlated as quantum mechanics permits anything to be, then neither of them can be correlated with anything else at all. Not weakly, not partially. The capacity is used up. This is a theorem with a slightly unfortunate name, and it is among the most rigid results in the subject. Maximal entanglement is strictly a 2-body arrangement. Now take a photon leaving an old black hole and ask what it must be entangled with. 2 separate parts of the accepted picture answer that question, and they return different answers. Unitarity supplies the first. If information is escaping, the entanglement entropy of the radiation has to be falling. The curve has to be on its way back down. That descent happens because each newly emitted quantum purifies what came before it, cancelling the correlations that accumulated earlier, which requires the new photon to be maximally entangled with the early radiation, the vast cloud of it that departed across the preceding age of the universe. The smoothness of the horizon supplies the second. Empty space at short distances is not inert. The quantum fields in a vacuum are correlated across every point, so that a mode just on one side of any surface you care to draw is entangled with its counterpart on the other side. And this is not an incidental property of the vacuum. It is what makes the vacuum a vacuum. For the region around the horizon to be ordinary empty space, the outgoing photon must therefore be maximally entangled with its partner just inside. 2 demands on the same photon for maximal entanglement with 2 different systems. The theorem forbids it outright. One of them has to go. Dropping the second carries a consequence that cannot be waved away because the entanglement across the horizon is not a description of the vacuum. It is the vacuum. Cut those correlations and what is left is not empty space with a feature missing. What is left is a violently excited state, an enormous concentration of energy sitting precisely where the boundary is, produced not by adding anything, but by removing the thing that kept the region quiet. That is the firewall. Nobody built it, and nobody proposed installing it. It is the residue, the thing that automatically occupies the horizon the moment you insist the outgoing radiation be entangled with the other partner. Nothing survives contact with it, and on this reading, it exists at every black hole in the universe that has passed the halfway point. What that costs is the oldest idea in general relativity. In 1907, working as a patent examiner in Bern, Einstein had a realization he later described as the happiest thought of his life. A person falling freely does not feel their own weight. Gravity, locally, is indistinguishable from the absence of gravity. There is no way to determine from inside a falling box whether the box is falling or floating, and no local experiment detects a gravitational field at all. That single observation is the seed the whole theory grew out of, and it is the reason the horizon is supposed to be unremarkable. A horizon is not a place. It is a global fact about where light can eventually get to, and nothing local is meant to mark it. A firewall marks it. It gives the boundary a location, a temperature, a physical character, an inside and an outside distinguishable by anything that arrives. It converts the horizon into a place which is exactly what Einstein's happiest thought says cannot occur. So the four assumptions resolve into a choice, and the choice is between abandoning quantum mechanics, abandoning locality, or abandoning the founding intuition of general relativity. The firewall is what remains if the first two are kept. The reception was not warm. Raphael Bousso at Berkeley described his first reaction as, "You've got to be kidding," and then, having worked through the argument hunting for its flaw, conceded that it had the makings of a mighty fine paradox. At an informal gathering at Stanford, Preskill called the idea odious. Polchinski himself thought it was a little crazy, said so, and put his name on it regardless. Which is the part that has since been lost. The firewall is remembered as a proposal, a claim about what black holes are actually like, the sort of thing that generates headlines about walls of fire at the edge of the universe. That is close to the reverse of what the paper does. Nobody who wrote it believed in firewalls. The argument is structured as a demonstration that something in the accepted picture is broken, and the firewall is the wreckage left in your hands if you refuse to surrender anything else. It is not a description of nature, it is an alarm. And what made it so alarming is that after 14 years of people hunting for something better, it has remained the least radical option on the table. The attempts to escape came immediately, and several were serious. Daniel Harlow and Patrick Hayden observed that the argument requires somebody to actually carry out the comparison, to extract the entanglement between the late photon and the early radiation, which is a computation, not an observation. They estimated how long that computation would take and found it exceeds the remaining lifetime of the black hole. The contradiction is real on this reading and permanently beyond verification, which is an argument with a familiar shape by now. Others proposed that the interior is not a separate system in the first place, that the modes behind the horizon are assembled from the same degrees of freedom as the radiation, so the photon's two partners are one partner, and nothing is violated because there is only one relationship. None of it has closed the question, and none of it has been shown to be wrong. The paper went out in the summer of 2012, and in 14 years the field has worked around it rather than through it. Nobody has taken it back. Suppose the boundary isn't there. Not that it is permeable, or that something unusual happens at it, or that the physics nearby needs a correction. Suppose there is no horizon at any point, no surface of no return, no region where light stops being able to leave, nothing in the geometry corresponding to the feature this entire subject is named after. Suppose the object simply ends before it gets that far, in an ordinary way, and the horizon is a fiction produced by looking at it from too far away. That is a serious position, held by serious people, and it has been on the table for 24 years. It comes out of string theory, and the route to it begins with the most convincing thing string theory has ever done. In 1996, Andrew Strominger and Kumran Vafa took a particular kind of black hole, a highly idealized one, its properties chosen to keep the mathematics tractable, and counted its microscopic states directly, not estimated, counted by enumerating the configurations of strings and membranes that could assemble into an object with those characteristics. Then they compared the total against the entropy Bekenstein had proposed and Hawking had confirmed, the one fixed by the area of the horizon. The numbers matched exactly. For the first time, the entropy of a black hole had been derived from an underlying count of actual things rather than asserted by analogy. Whatever else string theory has failed to deliver, that result is genuine and nobody has explained it away. Samir Mather at Ohio State asked the follow-up question, which turned out to be far less obvious than it sounds. If those microstates exist and can be counted, what do they look like? What is the shape of space-time for one of them individually, rather than for the ensemble? Working through the simplest cases, he found that they do not look like black holes at all. Each individual microstate is a geometry containing no horizon and no singularity anywhere in it. The space-time runs inward and then closes off smoothly like the end of a finger in a glove at a radius just short of where the horizon would have formed. There is a surface, there is nothing behind the surface because the geometry stops. A black hole on this picture is what you get by averaging over an unthinkable number of such objects and losing the ability to tell them apart. The horizon and the singularity are both products of the averaging, real in the way that the temperature of a gas is real, and no more a description of any individual configuration than temperature is a description of any individual molecule. If that holds, the paradox dissolves rather than gets solved. A fuzzball radiates the way any hot object radiates, from its surface, correlations intact, carrying out the details of what it is made of. There is no interior for anything to be lost in. Nothing crosses anything at all. It also satisfies the demand Mather himself had established, that whatever repairs this has to be a change of order, 1, occurring at the horizon scale. A fuzzball is precisely that, and it manages it without the wall of energy. Mather has argued that something arriving at high speed would find the surface behaving to a very good approximation like an ordinary horizon. The structure is present, and it does not announce itself violently to anything moving fast enough. What has actually been demonstrated is a good deal narrower than the ambition, and his own review articles are candid about it. The explicit geometries, the ones written down and checked, describe black holes that are supersymmetric, extremal or close to it, and usually living in more than 4 dimensions. They are objects chosen because the mathematics can be made to cooperate, and they are not the objects sitting at the centers of galaxies. The counting is done in a limit where the strings interact only weakly, and it remains genuinely unclear what these configurations become once the coupling is strong and gravity is pulling properly on itself. The number of individual microstate geometries anyone has managed to construct also falls a very long way short of the number required. Not a modest shortfall, but a gap of many orders of magnitude, and one that will not be closed by grinding through further cases. So the position is a specific and rather beautiful proposal, verified in the corner of the problem where verification happens to be possible, with no demonstration that it reaches the corner everybody actually cares about. It might well be right. 24 years on, nobody can show that it is. The other approach starts from the opposite end and arrives somewhere just as strange. John Wheeler, who named a great deal in this field, also gave the 3-number theorem its popular form. Black holes, he said, have no hair. Everything that distinguishes one quantity of collapsing matter from another gets shaved away in the process, leaving 3 bare numbers and nothing else. The phrase lasted 50 years because it was accurate. In 2016, Hawking published a paper with Malcolm Perry and Andrew Struminger arguing that it isn't. The argument runs through symmetry. Strominger had spent years establishing something unexpected about the far edge of spacetime, that the region infinitely distant, where radiation eventually ends up, carries an enormous symmetry structure. Not the handful of symmetries anyone had catalogued, but an infinite family of them, one for every way of adjusting the boundary out there. And symmetries come with conservation laws. That correspondence is among the deepest results in physics, and it is not optional. Every continuous symmetry of a system produces a quantity that cannot change. An infinite family of symmetries produces an infinite family of conserved quantities, which means the number of things a black hole can carry is not 3. It is unbounded. The additional charges are held by what are called soft quanta, photons and gravitons of exactly zero energy, which cost nothing whatsoever to add and which nevertheless alter the state of the system. Matter falling toward a horizon on this argument implants a record of itself in those zero-energy modes, and the record stays at the boundary, available in principle to be read back. There is a physical face to this, and it can be measured, which makes it the most concrete thing in this chapter. When a gravitational wave passes through a region, the standard picture is that space stretches and squeezes and afterward returns to how it was. It does not quite return. Two freely floating masses, once a wave has gone by, are left permanently displaced relative to where they began, not oscillating, but shifted, and staying shifted. It is called the memory effect, and it is exactly the physical signature of those symmetries at infinity. The passing wave has moved the universe from one boundary configuration into a neighboring one, and the displacement is the record of the move. The effect is too small to have shown up in any single detection so far. Adding up many events may reveal it, and the next generation of instruments should manage it outright. If it is found, it will be the first direct evidence for the structure the soft hair argument stands on. What the argument has not done is close the problem, and the objections arrived quickly. Having an infinite number of extra charges is not the same as having enough of the right ones. The requirement is specific. The black hole needs enough distinguishable states to account for its entropy, and those states need to be correlated with whatever fell in. Nobody has shown that the soft charges accomplish either. A follow-up paper 2 years later attempted the counting head-on and got some distance with it, under restricted conditions. The sharper criticism came from Raphael Bousso and Massimo Parati, who argued that the hair is trivial, that these charges are fixed entirely by what is outside the black hole, that they can be stripped away by a suitable change of coordinates, and that they therefore carry no information about the interior at all. If that stands, the hair is perfectly real and completely useless. The exchange has not been settled either. Set the two proposals beside one another, and the thing they share is not obvious from the descriptions. Both are attempts to stop the horizon being what it has been taken for across a century. One removes it altogether and puts a surface in its place, an object with an outside and nothing behind it, closer to a star than to a hole. The other leaves the boundary standing and covers it in an infinite quantity of writing that carries no energy, so that what you would find there is not blank after all but densely inscribed, in a medium you cannot spend and cannot weigh. Neither has been shown to work. Both have been pursued for years by capable people, and both are still described in the literature with words like conjecture and program rather than result. That is not a criticism of anyone. It is a report on where 50 years of very good work has arrived, and if you find it unsatisfying, so does everybody involved. What is worth keeping is how far the acceptable answers have travelled. In 1971, the question was which 3 numbers a black hole carries. The serious options now include the horizon not existing, the horizon being covered in an infinite amount of weightless writing, and a wall of energy that nobody wants. Those are not adjustments to a picture. They are different objects. Mathieu's first papers on this appeared in 2002. Soft hair arrived 14 years after that. And the strangest suggestion of the lot had been sitting in the literature since 1935 in 2 papers written by the same man and published 2 months apart, who never once suggested they had anything to do with one another. In 1935, the Physical Review published 2 papers by Albert Einstein. The first appeared in May, the second at the beginning of July. Nathan Rosen's name is on both of them. Neither paper mentions the other, and for 68 years nobody had any reason to suppose they were connected. The May paper is among the most famous documents in the history of science, and it was written as an attack. Einstein, with Rosen and Boris Podolsky, set out to show that quantum mechanics is incomplete. The argument turns on a situation the theory permits. 2 particles prepared together and then separated by any distance you care to arrange, whose properties stay correlated in a manner with no classical explanation available. Measure one, and you immediately know something about the other, however far apart they have travelled. Einstein's position was that this is absurd, and that the absurdity points at a missing piece, that the particles must have been carrying their properties all along, and the theory is simply failing to describe them. He called the alternative spooky action at a distance, and he offered the phrase as a reason to reject it. He was wrong. 30 years later, John Bell worked out how to turn the question into an experiment. The experiments were performed, and they came out against him repeatedly and by wide margins. The Nobel Prize in Physics was awarded in 2022 to 3 people for that work. The phenomenon Einstein described in order to discredit quantum mechanics is now called entanglement. It is about as thoroughly confirmed as anything in the subject, and his paper remains the standard citation for it. The July paper had a different purpose, and it also failed. Einstein and Rosen were attempting to build elementary particles out of geometry alone, to describe an electron as a feature of space-time rather than an object sitting inside it. What they turned up along the way was that the equations describing a black hole can be rewritten so that they look like 2 separate regions of space joined by a narrow throat. They called it a bridge. The program it belonged to went nowhere, and the bridge is the reason the word wormhole exists. What follows from setting those 2 papers beside each other is a claim about the ground you are standing on, and it is worth stating plainly before the argument that supports it. The proposal is that entanglement and geometry are the same thing, that when 2 systems are correlated in the quantum sense, they are also connected, not metaphorically, not as a manner of speaking, but joined by an actual passage through space-time, however small, and that the space between you and anything else is not a container the 2 of you happen to be occupying. It is a summary of how strongly you are correlated with it. Distance, read this way, is what weak entanglement looks like from outside. The smooth, continuous fabric everything appears to rest in is woven rather than built. The proposal is called ER equals EPR, after the initials on the 2 papers, and it came from Juan Maldacena and Leonard Susskind in 2013. Their starting point was a solution everybody already accepted. Take 2 black holes far apart, prepared in the particular state where they are maximally entangled with one another. Write down the geometry and you find they are connected. A bridge running between their interiors, precisely the throat from the July paper. That bridge is useless for travel. Nothing crosses it in either direction, because it stretches faster than anything can move through it. 2 observers falling in from opposite sides can meet one another inside, briefly, and neither can send word of the meeting anywhere at all. The connection is entirely real and cannot be used for anything. What Maldacena and Susskind proposed is that this is not a quirk of that special solution, but a general fact. Every entangled pair is connected in the same way. Two entangled photons in a laboratory in Vienna are joined by a bridge, a tiny one, a quantum one, not describable by any geometry anybody currently knows how to write down, and the same kind of object. Entanglement and connection are two names for a single structure. Some evidence had arrived 3 years earlier from Mark van Ramsdonk in Vancouver, working in a setting where the mathematics can be carried out exactly. He took a space-time, divided it conceptually into two halves, and asked what becomes of the geometry when the entanglement between the halves is reduced. The connection between them narrows. Reduce it further, and the throat pinches down. Take the entanglement to zero, and the two regions come apart altogether, not separated by a great distance, but disconnected, with no path between them of any length whatsoever. Two universes, where a moment before there had been one. Space, in that calculation, is held together by correlation. Remove the correlation, and it does not stretch. It tears. The reason this drew the attention it did is that it landed a year after the firewall and offers a route around it. The firewall argument requires the late photon to be maximally entangled with two different systems, the early radiation on one side, the interior on the other, and monogamy forbids exactly that. If the entanglement with the early radiation simply is a geometric connection into the interior, then there are not two systems. The radiation and the interior are joined. One relationship is being described twice from two directions, and nothing is violated because nothing is being shared. Underneath all of this sits the result that persuaded most physicists information escapes in the first place, and it has no direct connection to black holes at all. In 1997, Maldacena wrote down a correspondence between two theories that have no business being related. On one side, a theory of gravity operating inside a particular kind of curved space. On the other, an ordinary quantum theory containing no gravity whatsoever, living on the boundary surface of that space, in one dimension fewer. His claim was not that the two resemble one another. It was that they are the same theory written in two languages. Every state on one side has a translation on the other. Every process corresponds to a process, and any question askable in one description has an exact answer waiting in the other. That paper is the most cited in the history of high-energy physics, and it settles the information question in a single move, provided you accept it. The boundary theory is an ordinary quantum theory. It is unitary in the plain way that all such theories are unitary. It contains no mechanism at all for destroying information, and nobody has ever suggested otherwise. So if a black hole forms somewhere in the interior and evaporates completely away, that entire history has a translation into the boundary language, where it is described by something incapable of losing anything. The information survives in the bulk because it survives on the boundary, and the two are not two accounts, they are one account. There is a difficulty with this, and it has never gone away. The correspondence works in a specific kind of space, one curved the wrong way, shaped so that it has a boundary at infinity which light can reach and return from in a finite time. It behaves, in effect, like a box, and that structure is what makes the whole arrangement function, because a boundary theory requires a boundary to live on. Our universe does not have one. The expansion is accelerating, driven by dark energy, which corresponds to curvature of the opposite sign, and the shape that produces is not a box. It has no boundary of the required kind, anywhere, at any distance. Decades of effort have gone into finding an equivalent correspondence for a universe built like ours, and nothing has been established. So the strongest argument that information is preserved, the one carrying most of the weight, the one that actually convinced the field, is a theorem about a universe next door to this one. Almost nobody seriously doubts that it applies here. Nobody has shown that it does. Everything in this chapter is a conjecture. The wormhole proposal is a conjecture. The correspondence is a conjecture, extraordinarily well supported and still unproved, and the argument the two of them combine to make is an argument by translation rather than a derivation of anything. What arrived in 2019 sat on an entirely different level. Somebody did the calculation, not a proposal about what two things might have in common, but an actual computation from the equations of the quantity in dispute. And what came out of it was a line that rose and turned and descended to zero in precisely the shape Don Page had drawn 26 years before. What does it mean to have an answer nobody can explain? That question is not being asked rhetorically here. It is the actual condition of the field, and the people inside it describe it in those terms without needing to be pressed. Raphael Bousso, who has spent a career on this problem, put it about as plainly as it can be put. We now can compute the Page curve, and I don't know why. The calculation appeared in the spring of 2019 from two groups working independently and arriving within weeks of one another. One was Jeff Pennington, then a graduate student at Stanford working alone. The other was a collaboration of four, and two of those names are worth pausing over. Ahmed Almhairi and Donald Marolf had been half of the group that took complementarity apart in Santa Barbara 7 years earlier. The same hands that demonstrated the accepted picture was broken produced the first calculation that made the curve bend. What they did rests on one idea, and the idea is strange even measured against everything preceding it. Suppose you want the entropy of the Hawking radiation. The obvious procedure is to look at the radiation and calculate, which is what Hawking did, and which gives the line that rises forever. The rule these groups applied says the obvious procedure is incomplete. When you compute the entropy of the radiation, you are obliged to consider including, as part of the radiation, certain regions of space-time that are not in the radiation. You work through the candidates. You take whichever gives the smallest answer. And the rule contains a term penalizing the boundary of any region you add, so that including one is never free. Early in the evaporation, no candidate beats the obvious choice, and the answer is the rising line. Past the halfway point, one does. A region deep inside the black hole, the island, starts producing a smaller total when it is counted as belonging to the radiation. So you count it. And in the moment you do, the entropy stops climbing and begins to fall, in precisely the shape Page had drawn. What makes this uncomfortable is not the arithmetic. It is what the arithmetic asserts. The island is a region of space-time inside the black hole, sealed off from everything outside by a boundary nothing crosses, and the calculation says it is already part of the radiation. Not that it will eventually be encoded there, that it is, at this moment, correctly described as belonging to a cloud of photons scattered across light years of empty space. The obvious objection is that the rule was borrowed. It had come out of holography, developed for other purposes and tested in settings where the mathematics behaves, and applying it here looks a great deal like assuming most of what was supposed to be demonstrated. That objection was answered the following year, and the answer is where this stops being comfortable for anyone. Calculating an entropy directly from first principles uses a standard technique. Make several identical copies of the system, compute something about the collection, then continue the result mathematically back down to a single copy. In ordinary physics, this is unremarkable. Do it in gravity, and something unexpected happens. Gravity sums over geometries, so once you have several copies, you must include not only the arrangement where they sit separately side by side, but also the arrangements in which they are joined, where a passage runs from the interior of one copy into the interior of another. These are the replica wormholes, and nobody inserted them deliberately. They are simply present in the sum. and they had gone unnoticed for 40 years because nobody had thought to look. Include them, and the island rule falls out. The formula that had been borrowed turns out to be derivable, directly from the gravitational path integral, with no holography assumed anywhere. And nobody can tell you what those wormholes are. They connect different copies of the same universe, which is not a description of any object anyone knows how to interpret. They may be real structures. They may be artifacts of the bookkeeping, a property of how the sum was taken rather than of anything that exists. So the position as it stands is this, and it deserves care because it gets reported wrongly in two opposite directions depending on who is doing the reporting. The result is real. It is not inflated, and it is not a technical footnote. After 43 years in which nobody using any method could make the curve bend, two independent groups made it bend, and within a year, two more derived the rule from underneath. That is the most substantial progress on this problem since Hawking stated it. What has not been achieved is an explanation. Nobody can point at a photon leaving a horizon and say where its correlation with the earlier radiation came from. Nobody can describe the mechanism. The calculation produces the right number and supplies no account whatsoever of the physical process generating it. And the people who did the calculation are the first to say so. Busso's remark is the compressed version. Raghu Mahajan on the wormholes. It's hard to answer what's physical and what's unphysical because there's something clearly right about these wormholes. Steve Giddings has questioned whether summing over connected copies of a universe is a legitimate operation at all, whether it sits inside the rules of quantum mechanics as anybody understands them. Renate Lol, watching from the direction of a different approach to quantum gravity altogether, was blunter. I see people make the same hand-waving arguments that were made 30 years ago. And Pennington has described a disappointment that is worth understanding properly because it inverts what the entire field had assumed. The expectation across 4 decades was that this problem was a door, that resolving it would require, and therefore expose, the microscopic theory of quantum gravity, that the question could not possibly be answered without first discovering what space-time is actually made of, and that the answer would arrive with a theory attached to it. It didn't. The calculation was carried out in semi-classical gravity, the old approximate framework everybody already had, with no new fundamental theory involved at any stage. The door opened without the key, which is a result, and it is also the quiet loss of the thing a great many careers had been pointed at for a generation. A review published in the spring of 2025 lays the position out carefully. The island results, it says, are suggestive rather than definitive. They show how information could be preserved without settling whether it is. It lists what remains open, and the list is considerably longer than the summaries suggest, and it closes on a line with an exclamation mark in it that reads as faintly wistful. Perhaps there is still much more to say about Hawking's paradox. 2 months ago, in June, a headline announced that scientists may have finally solved the black hole information paradox. The paper underneath it is a legitimate piece of work in a legitimate journal, proposing that black holes stop evaporating just short of the end and leave remnants behind. Objects around 10 billion times lighter than an electron, holding everything that fell in, arising out of a 7-dimensional geometry that reduces down to the 4 dimensions we can see. The paper is properly hedged. It states that the proposal sits beyond the reach of any accelerator now in existence and offers no experimental support. The headline said, "Solved." That is not the author's word, and it is worth noticing as a mechanism rather than as a complaint, because this happens roughly once a year and has been happening for 50. A specific proposal, labelled speculative by the people who made it, turns into a resolution somewhere in the passage between the journal and the reader. The calculation works. Why it works is not known. 50 years in, that is where the argument stands. There is a particular kind of telephone call where one person knows something the other doesn't, and the one who doesn't know is the one making the call. In the first week of March 2018, Malcolm Perry rang Cambridge with an update. He had been working with Andrew Strominger and a young researcher named Sasha Hacko on the follow-up to the soft hair paper, the attempt to do the counting directly, to show that those infinite conserved quantities at the edge of space-time could hold as much as a horizon requires. The work had reached a point worth reporting, so he called his collaborator to say where it had got to. Perry did not know how ill Hawking was. Nobody had told him, and it is not clear that anybody knew precisely. He delivered the update the way you deliver an update to somebody you expect to be speaking to again the following week. It appears to have been the last scientific conversation Stephen Hawking had. Perry said afterward to a newspaper, "The thing that has stayed with me out of this entire 50-year argument, and it runs to 5 words." He knew the final result. Hawking died on the 14th of March. The paper went up 7 months later in October with his name on it. He never saw it in print, and he had already been told where it came out. 6 weeks earlier, the 2nd of February 2018, Joseph Polchinski died at his home in Santa Barbara of a brain cancer he had been fighting since 2015. He was 63. He had spent his last years working on the problem he had made worse, and he did not repair it. The two of them went within 6 weeks of one another, and they were not the first. John Wheeler, who started the whole thing running with a remark about teacups, died in 2008 at 96. Jacob Bekenstein, who took that remark away and thought about it for a few months and came back with the answer everything else grew out of, died in 2015 at 68. Everyone who began this is gone. The question is not, which leaves the objects. The page signed in Pasadena sits in a museum in London, typed 2 handwritten signatures and a thumbprint pressed by a man who could no longer hold a pen onto a contract about whether the universe keeps a record of things. He lost that bet in public, in a crowded hall, in front of cameras, using an argument that almost nobody accepted. He was probably right. Kip Thorne, who signed the same page on the same side, has still not conceded. 29 years. He was explaining his reasons out loud as recently as 2 years ago, and those reasons have aged rather better than the argument that was supposed to have settled the matter. The Encyclopedia is presumably on a shelf somewhere in Pasadena. It was always the joke and the argument at once, a book chosen precisely because books give back what is put into them, handed over to settle a dispute about whether anything else in the universe does. Hawking's ashes were interred in Westminster Abbey in the June after he died, in the floor between Isaac Newton and Charles Darwin. There is a stone with his name and his dates on it, and beneath them an equation. It is the entropy formula, the one Bekenstein proposed and Hawking confirmed, tying the entropy of a black hole to the area of its horizon, the result that created the problem in the first place, and the one nobody has finished explaining. It has been cut into the floor of an abbey, and people walk across it every day, and it remains in the strictest sense an open question. In the autumn of 2025, the people who work on this held a meeting that ran 7 weeks. Not to announce anything. The stated purpose was to find out whether they agreed with one another, because the different groups had drifted so far apart that they had stopped being able to follow each other's arguments. 50 years in, the field convened to take an inventory of what it actually knew. The answer, roughly, was that the curve bends, and nobody is certain why. So stand back from all of it. The observable universe holds something on the order of a 1 followed by 104 zeros worth of entropy, and nearly all of it is already behind horizons. Everything that shines, every star, every galaxy, in every photograph anyone has taken, all the light that has ever arrived anywhere at all, is the thin, bright residue on the outside of a much larger and much darker accounting. That has been the case for billions of years, and nobody noticed until about 50 years ago. None of it has started coming back. Not one black hole anywhere has yet lost a gram. The background is still too warm and will stay too warm for another 300 billion years, and only then does the first of them begin to shrink, and then there is 10 to the 67th years of shrinking to get through, with the halfway point buried somewhere inside it where the correlations start to surface, in a cosmos containing nothing that could be called a witness. The evidence, as it stands in the summer of 2026, leans toward preservation, not proof. The curve bends when you do the calculation properly, and the rule behind it has now been derived from underneath by more than one root, and the boundary description of the universe contains no mechanism for losing anything. Set against that, nobody can say how, nobody can identify the process, and the strongest argument comes from a universe shaped differently to ours. That is the position. It is a great deal better than it was, and it is not finished. If it holds, then the answer to the question this began with is that the story is still there, not accessible, not readable. Written into the correlations between photons that will not finish arriving for longer than the universe has so far existed, requiring a reader who has been collecting since the beginning and has somewhere to put it all. The book that went in is intact in the only sense the universe recognizes, which is that nothing which happened has stopped having happened. There is no good word for what that makes the universe, and I have not found one you could use without immediately taking it back. It is not an archive, because an archive implies somebody keeping it, and there is nobody. It is not a witness. A witness attends, and nothing here attends to anything. It is not memory either, because memory belongs to something capable of retrieval. What the universe appears to have is a property with no name attached to it. It does not lose. Whatever has occurred stays encoded in the arrangement of everything that came afterward, completely, permanently, and to no purpose at all. Every conversation, every collapse, every star that formed and burned and failed, every book that went past a horizon somewhere in the last 13 billion years, all of it still specified in a form so thoroughly dispersed that reading it back would mean being larger than the process that wrote it down. A complete record, kept by nothing, for nothing, indefinitely. I have gone back and forth for a long time over whether that is the loneliest fact available or the most reassuring one, and I have stopped expecting to settle it. What I notice is that the two are not really in competition. The universe is not indifferent to us the way a person can be indifferent. That would require having considered the matter. It is simply built so that nothing goes missing, and we arrived inside it briefly, able to look at the arrangement and wonder what it means. So this is where it rests tonight, and it will very likely still be resting here in a year. A man in Princeton wondered whether he could get away with a small crime against thermodynamics, and his student went away and came back and told him he couldn't. Somebody set out to prove the student wrong, and found instead that black holes glow, and then followed his own discovery to the place where it broke quantum mechanics, and spent the remaining 40 years of his life there. 50 years of very careful people working on a question that cannot be tested, will not be observed, and does not begin to resolve itself for 300 billion years. They have got the curve to bend, which is not nothing, and it took them 43 years. And the answer that seems to be emerging quietly, without anyone quite being able to explain it, is that the universe does not throw things away. Not the book, and not the star that fell in before there were any books, and not the tea that Wheeler was joking about, and the universe was not. All of it stays, scattered past retrieval, written into correlations nothing will ever hold, spread across radiation still arriving long after the last light has gone out anywhere. Which is a strange thing to find at the bottom of a subject named for the places where things disappear. You are very small in this. That was rather the point of the exercise, and it is meant kindly. The things weighing on you tonight are real? They are also happening inside a system that has never once mislaid anything. Whatever you did today is still here. It will be here tomorrow. It will be here when there is no tomorrow left to have it in. The universe is keeping it. Not for you, just keeping it. Sleep well. Good night.